Okay, lecture 48, free energy and equilibrium constants. So write the thermodynamic equilibrium constant for the following reactions. So we talked about Kp many lectures ago, and then we just talked about briefly comparing Kp to Kc, and then we forgot about it. And we're going to talk about the thermodynamic equilibrium constant for a minute or so, and then we're going to forget about it until we get to the next chapter. So we just keep kind of piecing things together. We're going to really need this term down the line. Now, whoops. Let's see. So they just call it K, not Kc or Kp, because it incorporates both terms. If it's a concentration, we put it in square brackets. So it's the same, we're just making an equilibrium constant expression, but if we have aqueous, it goes in constant, we put in the square brackets. If it's a gas, we use the partial pressure. And water doesn't count here. And you say, well, why would we do that? That looks more complicated. Well, we're not there yet. So just be able to do this. You should be able to just think in terms of the thermodynamic equilibrium constant, where this is liquid, this is gas, so this is PCO2. This is, and I'm not trying to be mysterious, it's just that really there's no reason to get into why we're doing this right now, other than to say that if we put it into this form, then when we're in standard conditions of 1 molar, then this will drop away. But 1 molar concentration won't guarantee 1 atmosphere pressure. So if we're in standard conditions, next chapter, we can just, this will be 1 molar, this will be 1 atmosphere. If we converted 1 atmosphere over to concentration, which we could do for a gas, it wouldn't be 1, we wouldn't have a 1 out in front. So it will just simplify things. So if you didn't understand that at all, don't worry about it. Just be able to do this. We'll talk about how we use it in the next chapter. Okay, I worked out most of the, well, all of the calculations just to speed things along. Calculate the free energy in K for each of the following reactions. So here are the delta G's. And what I'm trying to do here, we can take the delta G value, the free energy of change of free energy for the reaction at standard conditions, and convert it to K. So we see there's a relationship between thermodynamics and kinetics. So we know that if a delta G is negative, that a very large negative number, then we expect it to be spontaneous. And we know that K must be a very large number for it to be spontaneous. So there must be some relationship there. And the equation that relates the two is right here. But first what we do is we get the delta G. So I did that out. And notice what we have here. We have HCl plus water goes to H3O plus and Cl minus. So what I'm going to be finding here is Ka for a strong acid. We've always said, well, the Ka is gigantic. And I threw out numbers of hundreds of thousands or millions, even billions. But here we're going to actually calculate it. So these numbers actually turn out to be the same because it's just water here with an H plus, and the delta H or delta G for H plus aqueous is 0. So these actually cancel each other out. We end up with this value, pretty large negative number, and then we put it into this expression. Make sure you have 8.31. Now, in the book, they kind of ignore they just put in the numbers. They don't use these moles here, because the moles cancel. We're just left with kilojoules. But this is per mole, because it's 1 mole of the acid. So we can put the mole back in if we want. That's not a problem. And we do that because this constant is joules per kmol. In the book, I noticed in one of the problems, they just kind of ignore it. And these K's are different than this constant here. This is capital K. This is a capital K, but it's units for temperature, so you got to be careful there. Then we solve for K. We end up with the natural log of K is equal to 14.5, so K is just E to the 14.5. And so K, which in this case, since it's for this acid, is Ka, is 1.98 times 10 to the 6th, so 2 million. So that's the Ka for hydrochloric acid. And if you knew that, you could certainly have put it into the expressions we talked about and pretended like this was an equilibrium that lies somewhere in between, but you'd find that if you ever used that K value for the previous 2 chapters ago, that you'd always end up with 100% product because of the size of that guy there. Okay, now this one I did out too. Ignore this up here. I made a mistake with the H3O plus. Now we got sodium carbonate plus 2 HBr goes to water, CO2, and two NABRs. I came up with a delta G of minus 103.6. Putting that into this value, we end up with a K value that's 1.42 times 10 to the 18. So this reaction, the reason it's so gigantic, even compared to a strong acid dissociation, is the production of this CO2. This reaction, if you put sodium carbonate into acid, will produce a bubbling of CO2 that will be very vigorous. And so the reaction is going to go way over to the right, because this CO2 then goes off into the air, assuming that it's not captured and we put it under pressure and force it back the other way. If it's free to leave, then this K should be a gigantic value. Now we can go the other route as well. Magnesium carbonate, we know what the KSP is for it, and that's just a K value. We call it KSP because we want to specify that we're talking about a solubility product. But we can certainly put that value in, assuming, and I've been assuming that temperature is 298. We'll always do that, except for the last problem we do here at a different temperature, just to show that it can be done. But normally we deal with the temperature at 298. Plug this value in, and we end up with plus 28.5 kilojoules per mole. And I did that out a couple of times. There's some error in the, this is actually just 1.0. Hold on for a second. So if you find the delta G using the delta G values of in the back of the book, delta G of formation values, you're going to have something that's different, but it's going to be off by less than an order of magnitude, and that's fine. That's just due to the uncertainty in this number, which is a very small number, and it's 1.0. And I just put the extra 0 in there, but because there's only two significant figures, that would show that there's a tremendous amount of uncertainty there, that if we change this slightly, we could really change that number. But just throwing that out there. And that's how you do it. Whatever K value you were given, you just put it directly into the equation and solve for delta G. Don't forget that negative in there. How does the temperature affect the spontaneity of a reaction? Okay, now, we see that we have delta H can be positive or negative. Delta S can be positive or negative. Now let's look at a couple examples here. If delta H were negative, I'm just going to put it as negative here, and then we have negative T, and yeah, let's do it this way. I'm going to just increase the size of this thing here so that we have, okay, so if delta H is negative, it's exothermic, well, T always has to be positive, and we have a negative here. And let's say that delta S is positive. So we just picked these to be the case. Then this is negative, these two are positive, and this is a negative term here. So this thing is always, or delta G is always negative. Or in other words, always spontaneous, no matter what the temperature is. Because T can be 0, I mean, and we don't normally work with anything that low as far as the temperature, but that would just get rid of this term, so this would be negative. But any T above 0 is going to be positive, so this term is always going to be negative. This one is negative, so delta G is always negative. So it's always spontaneous no matter what the temperature is. The other one that we can have is if this is positive, if this is endothermic, this is always going to be a negative sign here, this is always going to be positive, and then if delta S is negative, for instance, where we go from a more chaotic system to a more ordered system, this is always going to be positive. So I'm not putting any numbers in here, but whatever value this was, if it was positive, this was negative, and no matter what the temperature is, we'd always have a positive delta G, so it'd always be non-spontaneous. So these are two possibilities. Now what if delta H is negative, so it's exothermic, and the delta S is exothermic? So you can see that this term is going to be negative, and the whole thing is going to be positive. But if t is small enough, then it's going to be a small value. Let's say it's 0, then this term would be gone. It would be delta g would be negative. But since this whole term here is positive, and it depends on temperature, as the temperature gets larger, this term gets to be a larger and larger and larger positive value until eventually it becomes non-spontaneous. So this one, we can't say that it's one or the other depending on t. So at low t, it is spontaneous. At high t, let's see, sure. So it's at low, yeah, so non-spontaneous. Just make sure I got that right. This term is always, this whole thing is going to be positive, and the size of it is going to depend on temperature. As we keep going up and up, eventually this positive term overwhelms that negative term, and it becomes non-spontaneous. Now, that temperature might be 10,000 Kelvin before we get there, but we will eventually get there. So we have these possibilities. And then the last one is if delta H is positive, this is going to be positive, and if this is positive, then this whole term is negative. So at low t, when this term is very small, then it's going to be non-spontaneous. At high t, it's going to be spontaneous. So just the negative just indicates it could be one or the other here for delta g. So when this term is very small, then it's going to be non-spontaneous because the delta H is going to overwhelm this term. But we can make t as high as we want. So eventually t gets so large that this negative value is larger than the positive value. It becomes spontaneous. Then, if you want to know when does it shift over, so for each of these, there's a point where it's one thing, and then as the temperature goes up, it shifts over into the other, from spontaneous to non-spontaneous, or non-spontaneous to spontaneous. Well, that would occur when, just as whatever temperature this is, this equals 0. That's when we're just on the cusp, just when we're shifting from one to the other. So if we solve for t, then t is equal to delta H over S, point at which we change from spontaneous to non-spontaneous, or non-spontaneous to spontaneous, one or the other. We go from one form to the other. So let's take a look at a problem involving this concept. I did out a lot of this previously. So determine delta G for sodium solid changing to sodium chloride solid changing to sodium solid in chlorine gas at 298 Kelvin and at 2700 Kelvin. Okay, so we're going to do a little trick here. Here are the values that we have for sodium chloride, and we have delta G, delta H, delta, and then S. Now delta G, we can use this value at room temperature at 298, and we see that delta G is plus 384 kilojoules per mole. It's non-spontaneous at 298. Now, if we want to do this, and I should probably just rewrite this a little bit. If we want to find out the free energy at another temperature, what we do is we can take delta H standard minus T delta S standard and change the temperature. Now, really, that shouldn't be allowed. This is the true equation. We put this T here to indicate we're at a different temperature. This equation is only supposed to work at 298 Kelvin. However, delta H and delta S don't change very much with temperature. They are temperature dependent, but they don't change very much. So it is actually a pretty good approximation to use delta H here and delta S here and put in a different T to get your delta G. And that's what we do. Using this data, so that means that we can use this data here at 298 Kelvin, but if we want to do a different temperature, then we have to rely on delta H, and this should be formation, and SF standard. So this data will give us, I'm not going to go through the whole thing here, delta H is 400 and positive 400 kilojoules per mole. Delta S standard is 202 joules per kmol. I apologize, I just kind of was working on this in an awkward position when I was doing the, I had my cat on my lap and I was trying to eat breakfast, so these numbers aren't, they're a little scribbled, but these are the numbers from the back of the book, and normally I redo them, I just noticed that I hadn't, sorry about that, but these numbers are correct even if they're a little messy, and you can certainly get them out of the back of the book. So when we're dealing with a different temperature, then we can use this equation. We can use these values that we can get from our data, this data, but we can't use the delta G data because that's only for 298. But we can use the delta H and delta S data that's at 298, and then do that little trick where we just change the temperature here. And then we get delta G. This is going to be, we have to change to joules. We don't, or you have to change so that we have the same units on both sides. This is minus 270, 2700, 202, and we end up with minus 134 kilojoules per mole. So now it is spontaneous. Before, at 298, delta G was plus, what was it, 200, plus 384 kilojoules per mole. Now it's minus, so now it's spontaneous. So we can see that we can alter a reaction, we can force it to become spontaneous by changing the temperature. We can also make it non-spontaneous by changing the temperature, depending on what we want. Now, as we said, that as it goes from positive to negative, there's a point where it's 0. And right when it's 0, it's about to change over from non-spontaneous to spontaneous. And if we rearrange this, like I did earlier, we end up with this expression. And we put in our numbers. And this will tell us exactly what temperature that we shift from spontaneous, non-spontaneous to spontaneous, and it's 2035 Kelvin. Now, if we ran the reaction at that point, we'd see that we wouldn't get much in the way of a product, because we're right on that cusp. We'd want to increase the temperature and keep increasing until we couldn't go up any higher. You know, our reaction vessel wouldn't allow it, or some other factor would get in the way. The higher the better in this case, because the higher the temperature, the more spontaneous it will be. The higher, the more negative the delta G would be. So, but this is the point where it shifts over.